Hi everyone, today we are going to learn new topics related to additions of a system of coplanar forces. In the previous lectures, we have learned how to perform factor operations of two or more force factors, and also to find components of a force factors with respect to two axes that are not perpendicular to each other. Okay, and in these new topics, we are going to narrow down our discussions, learning how to perform those factor operations using rectangular components, or in other words, it's the two-dimensional Cartesian components of the force factors. And the terms that I use in here is coplanar forces. I think it is more suitable to use the terms concurrent forces, because the forces that we are considering in here, to some extent we can assume that they are acting from the same location. Okay, and then let's get started. So I believe most of you have learned similar things related to what we are going to discuss in these lectures in physics class, but this is going to be a good occasion to just review what you guys have learned. Okay, let's say we have axis x and y, and there's an origin O, right? And then the unit vectors along the x-axis can be represented as I. Okay, the unit vectors along the y-axis can be represented as J, and noted that I use a hat over here to not to indicate that it is a unit vector. Okay, and let's say we have a force vectors, and let's call that force vectors as F1. Okay, the rectangular of components of these vectors, or in other words, the two-dimensional Cartesian components of these force vectors, can be obtained by projecting, right, the force vectors into the x and y axis, such that I will obtain F1x and F1y. Alright, and if this angle right here is theta, okay, we can express F1 as F1x I plus F1y j, and note that in here this is the magnitude of F1x and this is the magnitude of F1y. Okay, and we can obtain F1x in here by taking F1 cosine theta. Okay, and then F1y can be calculated as F1 sine theta. Okay, and the magnitude of the force vector F1 can be obtained by taking the square root of these vectors over here, which is F1x squared plus F1y squared. Okay, and theta, tangent theta, is defined as F1y divided by F1x. Okay, such that you can calculate theta by taking the tangent inverse of F1y divided by F1x. Right? And in this course there will be many problems in which there is a little triangle given in the problems to indicate the directions of the force vectors. Okay, so let's say that this is the little triangle right here, and this is A, this is B, this is C, okay? And let me try to resketch that triangle right here. So this is the little triangle, this is A, this is B, this is C, okay? And then when we consider another triangle right here, okay? If we consider another triangle in here, which is larger one, okay, we will have in here, the length in here is f1, the length here is f1y, the length here is f1x, and note that this angle is theta. Similarly, this angle right here is also theta. Okay, so by the principle of similar triangle, we can write an expressions that is very helpful to find the components of the force vectors without knowing what is this angle theta over here. Okay, so we know that f1x divided by b is equal to f1y divided by a is equal to f1 divided by c. So in other words, I can calculate f1x by taking b over c times f1, and f1y is a over c times f1. Okay, so I guess this is some of the equations formula that will be helpful when we perform the calculations. However, it is very important to understand how we come out this formula rather than on memorizing the formula itself. Okay, and then let's consider a second case right now. Let's just redraw it over here. So I have my x and y axis, okay, and then the unit vectors in I and j right there, and then I consider force here is F1, right? And then let's say that I have another force right there is F2. Okay, from these forces I can find that its component with respect to the x and y axis. Okay, so in here I have F1x, here I have F1y, right? And then here I have F2x, and then here I have F2y. Okay, so if I define a resultant vectors Fr as F1 plus F2, okay, note that we can express F1 as F1x I plus F1y j plus F2xi plus F2y j, okay, such that in here we will obtain Fr is equal to F1x plus F2x I, okay, plus F1y plus F2y j. Okay, and if I can call this as Frx, this is as Fry, okay, we can write a general expressions. Okay, Frx is sum of the forces in the x directions, and Fry is the sum of the forces in the y directions. Okay, so what does it mean? It means that if we have more than two force vectors, let's say 3 or 4, then these expressions right here will becomes f1x plus f2x plus f3x, for example, right? And then here will becomes f1y plus f2y plus f3y. However, it's noted that this is only can be written like this if fr is defined as f1 plus f2 plus f3. Okay, in some cases we will do factor difference rather than factor summations. In that case, what we need to do is just to change the sign in here. Okay, instead of using plus, we use minus. Okay, so for example, if fr is defined as f1 minus f2 plus f3, right? So frx is equals to f1x minus f2x plus f3x, and fry is equal to f1y minus f2y plus f3y. Okay, I think that's it for these lectures, and in the next lectures we are going to discuss the three-dimensional Cartesian components of a force vector. Thank you.